Hello geometry students, we are going to prove the Pythagorean theorem in this video, and we've done proofs of the Pythagorean theorem before using the area method, and I just want to show how we can prove the same theorem without using area at all. And I actually prefer this method over the area method because we actually haven't talked about area yet up to this point in the course. We're assuming a lot of things that we haven't proved yet. This particular proof that I'm going to show you now assumes nothing about area and uses concepts like similarity and right triangles that we've already developed fully in this course. So let's get started. I have a picture here and I have a given. This is the picture that I'm given. Triangle DEF is a right triangle, and I have to show somehow that a squared plus b squared equals c squared. So to do this proof, the first thing that I'm going to do is draw in the altitude of this right triangle, and I'm going to draw it straight to the hypotenuse. Okay, and I'm going to name this one, I see DEF, I'm going to call this one G. Okay, and also to help me just reference things a little bit better, I'm going to have some names here. So I already have A and B and C, so we're going to call this one X. We're going to call this Y, and we're going to call this Z. Okay, so I just got some, so the small case letters represent lengths, and the large letters, the capitalized letters, represent distances. Okay, and this C here should really be a smaller c. Okay, so that make things a little bit more clear. Okay, so first thing that I can show here is that I've got some triangles that are in fact similar to each other. So we've seen this theorem before. We have two right triangles in this picture that are similar to each other. That's this left one right here is in fact similar to the entire big right triangle DEF. So let me write this out. Triangle DEF is similar to triangle DGE. And I'm going to cite this as theorem 7.5, similar right triangles. So if you're not familiar with this theorem, you can look at one of the other videos in the same chapter, and it will go through and explain why the big triangle DEF is in fact similar to the triangle DGE. So from here I can deduce the proportionality statements. So I can say that DE, so that's on the first triangle here, that compares to DG. And that's equal to DF. So now I can look at these 2 points. Look, D and F of the first triangle is also comparable to D and G of the second triangle. And this is the definition of similar triangles. So if the triangles are similar, I can write a proportionality statement. And these dots and dashes right here, I'm just pointing these out so you can see a little bit better. They don't actually mean anything. Okay. So now I'm going to substitute in the actual lengths of these statements. So I'm going to show you that here. DE is actually A, so A goes on the numerator there. DG is Y, so A over Y is equal to DF, which is C, over DE again, which is A. And this is just substitution. And then I can cross multiply these two. So I got A squared is equal to Y times C. Okay. So that's one statement that's very useful to me. And I've used one similarity of the small triangle and the large triangle here. Now I'm going to continue this proof by showing that the medium triangle, or the one on the right, is also similar to the large triangle. Okay, so the next step of my proof, I am going to show that triangle, I'm going to use the fact that triangle DEF is in fact similar to triangle EGF. So this is just saying that the medium-sized triangle, or the one on the right here, is in fact similar to the large triangle, or the entire image that we have in front of us. And this again is theorem 7.5. Okay. So because these two triangles are similar, I can write a proportionality statement for them, just as I've done for the previous one. And in this case, I can write that DE, I can write that DE sorry, I don't want to use DE. I want to use something, I want to use a different side that's a little bit more helpful to us. So I'm going to use EF. Okay, so these two sides is going to be using a proportion with GF. So EF is the first one over GF, okay, is going to be similar or equal to DF, so that's the first one and the last letter here, and EF again. Okay, so DF over EF. And this is the definition of similar triangles. Okay, so if the two triangles are similar, then I can write a proportionality statement. So to continue with this proof, I'm just going to substitute in the actual lengths here. So EF on our picture is actually value, it has a value of B. GF is Z. DF is C. And EF again is B. Okay, so let me just show you the picture here so that it'll make a little bit more sense. Okay. So DF, sorry, so EF right here is B. GF is Z. And let me rewrite what we had before. Before we had that in step 6, let me write up here, I had the DF, sorry, a lot of letters here that gets mixed up easily. EF over GF is equal to DF over EF. Okay, so that's what we had in step 6, and you can see here on the picture that EF is B, GF is Z. Okay, so that's Z goes in here. DF, that's from here to here, that's C, and then EF again in this denominator is B. Okay, so that's B there. So all I've really done is substituted the names for the actual lengths. Now, and then I'm going to cross multiply and simplify here. So multiply this direction gives me B squared is equal to Z times C. And I want to sort of back it up a few steps. You can see from step 4 and step 8 that we have an expression for A squared and B squared. And I'm going to find a way to combine them together by using the reflexive properties. So I'm going to write this out that A squared plus B squared is equal to A squared plus B squared. And there's nothing wrong with that. I can definitely say that because this is the reflexive property. It seems silly, but is actually incredibly useful. Okay. And then I'm going to substitute. I'm going to leave the left side alone, A squared plus B squared. But the right side, instead of writing A squared, I'm going to write YC for this. And instead of writing B squared, I'm going to write ZC. Okay. So I left the left side alone, and I've substituted in the right side. substituting values for the right side. Okay, let me set this aside for a minute and just do a little bit of work here. So this is substitution. So the left, I have a squared plus b squared. The right side, I'm going to factor out c, and that leaves me with y plus z. So this is factoring. But if you look back at our original picture, y plus z equals c. See this? Y plus z is in fact equal to c. So I'm going to write this right here. Y plus z equals c. And this is really segment addition postulate. So taking this result here, since y plus z is equal to c, I'm going to take this one and substitute it in here. Okay. So from step 11 and step 12, I got a squared plus b squared is equal to c times c. This is substitution. Therefore, a squared plus b squared is equal to c squared. This is simplified. Okay. And there you have it. And notice here in this proof, we don't use anything about area. We've only used official theorems and postulates that we proved or we stated before in this course. And that's why this proof, I think, is a little bit stronger and is a little bit better of a proof than the proof using area, just for this point in the class, because we haven't really discussed what area really means. So now we know how to prove the Pythagorean theorem in two different ways.